Electromagnetic shielding. It is possible to screen the alternating magnetic field with the paramagnetic material and with conducting material. The magnetic material creates paths for magnetic field to pass, and the conducting material screens the magnetic field with the help of induced eddy currents. In this example, we will simulate the cylindrical shield made of two halves. Our task is to calculate the magnetic flux density reduction inside the shield. The external field will be applied using the boundary condition. Okay, let's start QuickField now. In QuickField, I create a new problem. Problem name is shield. Next. Problem type is AC magnetics. Frequency is 50 Hz. Every simulated device is a three-dimensional object. The shield features rotational symmetry, so I can use a two-dimensional model and simulate only a single cross-section. Model class is axisymmetric. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I'm going to draw it here from sketch. First, I will insert a rectangle with dimensions 31.5 by 63 millimeters. Anchor point here. Insert. Close. In axisymmetric problems, the axis of rotation is the horizontal one, and we should draw only the upper half of the cross-section. Switch to insert mode. Click and drag to draw a line. Then switch to select objects mode. Click and hit the delete button. Now zoom to fit. The wall thickness is 5 millimeters. So again, click to select, right click, duplicate selection, displacement by 5 millimeters down, and I will duplicate this edge, right click, by displacement of 5 millimeters to the left. Okay, let's zoom in, and I should remove this edge. Click and hit delete, and I will remove this vertex. This is only one half of the shield. I will move it to the right. Click to select, right click, move selection, displacement 1 millimeter to the right. Okay, and I should remove this line, and I will duplicate selection using symmetry and 90 degrees. Okay, now I have two halves of this shield, and the gap between these two halves is 2 millimeters. The shield is placed inside the region with an ambient magnetic field. We should draw this region's boundaries. So again, zoom to fit, switch to insert mode, and I will draw the air block boundary. Now let's assign labels. The labels will explain the geometric object's meaning and provide material properties. Switch to select objects mode, click the object to select, and type in the label name here, air. Let's zoom in. Switch the zooming mode off. Click to select. This is shield. And this block is shield to shield. Okay. QuickField automatically assigns proper boundary condition to the axis of rotation, and I will assign label to this boundary. I'm going to use this boundary to generate external magnetic field, so I will assign label source. Now let's provide physical properties for these labels. Double click the label name in the tree. Relative magnetic permeability of the air is 1. Okay. Shield is made of steel with relative magnetic permeability of 1000 and electrical conductivity of 10 megasiemens per meter. Okay. For the source edge, I will specify tangential magnetic field. For example, 100 thousandths. There is no other field source here, so the magnetic field lines should go parallel to this edge. They will have only the tangential component. And what will be the value of the flux density? I don't know. It depends on the distance from this edge to the axis. Let's try and see if we can correct the value later. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be constructed. Now save all problem files and solve the problem. Yes, take a look at the results. Here you can see the magnetic field lines and the color map of the current density. Let's zoom in. You see the magnetic field lines look broken. That's because of insufficient mesh density. Let me show you. I will zoom in and adjust the field picture, switch on the show mesh and switch off the color map. These green triangles are finite elements. Inside each element, the field distribution is considered to be linear, so you have the sharp corner here. Straight line, then another straight line. If we make the elements smaller, we can get smooth curves closer to reality. QuickField can automatically refine mesh in problematic zones. Open the geometry model. Again, I will zoom in. This is an initial finite element mesh, where finite elements sizes correspond to the geometric object dimensions. The smaller the object, the smaller the element, the larger the object, the larger the element. Now let's adjust the mesh to correspond to the field distribution. Click Solve and Refine. OK. And the mesh density will be automatically adjusted. OK, let's take a look at the result. Again, I will zoom in. Now you see the field lines are much smoother. You can run the solve and refine procedure again to get even better results. Now the field lines look good, they are smooth. Let's check some data. I will use the local values tool to measure the flux density outside. Local values, click here, and the flux density is 0.1257 and I need 0.139. What should I do? Open the source properties, multiply by 0.139 1.39. This is value I need to get, divided by the 0.1257. This is the value we have now. Okay, run the analysis again. Again, I will use the local values tool. Click here. Now you see the flux density is what I need. Now let's see the flux density value inside the shield. I'll click inside, and here is the flux density. You can adjust the field picture and switch on the color map of the flux density distribution. This way you can see better what happens with the magnetic field. 0.139. Okay. Almost uniform magnetic field outside. Let's zoom in. You see how the magnetic field penetrates through the air gap inside the shield. Now, what will happen if we narrow the air gap? Let's see. Open the geometry model. Click to select half of the shield. Right click. Move selection. I will move it to the right by 1 millimeter. Okay. Now the air gap is 1 millimeter. Build the mesh. Click OK. Save all problem files and solve the problem. Let's take a look at the results. Again, I will switch on the color map of the flux density distribution and set the maximum value to be 0.139. Okay. Now we see again the same uniform magnetic field outside, and if I zoom in, again the field penetrates through the air gap, but what is the magnitude of the magnetic field? Use the local values tool. It was about 0.04 when the air gap was 2 millimeters, but now 0.029. Well, what else you can do here? You can use the contour tool, draw the contour in any place and get the field distribution along this contour on the XY plot, flux density, and the exact values you can see in the table. You may note that in the shield the flux density is very high. That's because we have specified linear magnetic permeability. QuickField allows you to specify nonlinear magnetic permeability, which is close to reality. Specify the BH curve, and I will change the frequency to 0.01, so this will be DC. Let's solve the problem. You see, it takes more time because now the problem is nonlinear. It was simulated in 43 seconds. Now let's take a look at the results. Remember, this is DC. Let's zoom in. I will adjust the picture and switch on the flux density. Now this is the flux density in the shield, and you can adjust the field picture and switch on the permeability. If you zoom in, you can see which parts of the core are saturated. If you search for electromagnetic shielding on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. The simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.